Great. Thank you so much for the introduction, and thanks again to all the hosts for this really excellent webinar series. So I'm excited to talk to you guys today about some of the work that I've done in Professor Bao's group at Stanford during my time at, in the Bao group, developing conductive hydrogels for these next generation bioelectronic interfaces. So the motivation for my research is that there are all of these really exciting medical applications that kind of exist at this interface between electronics and biology. And what we've been seeing in recent years is that these applications are increasingly calling for electronics to be more and more intimately coupled with those biological systems. So for instance, neural implants, so electronics that are implanted in the brain, have already classically been used for deep brain stimulation to treat tremor in Parkinson's patients. And recently, we've been seeing companies like Neuralink that are expanding on this to create brain-machine interfaces that will allow people to control prosthetics with their mind. In other areas of the body, researchers like Takao Sameya at the University of Tokyo or John Rogers at Northwestern have developed all of these interesting conformal electronic devices to do things like assisting cardiac surgeons with more precise surgery, or even monitor the signals of babies that are in the ICU. And then even in regenerative medicine, now engineers have really had a lot of interest in exploring coupling electric fields with conductive materials to do things like promoting cells to differentiate into specific lineages, or promoting certain favorable morphologies or types of synchronization behavior between cells. And so despite all of these really promising advances, our ability to fully leverage electronic capabilities in biological systems is still limited by a very severe mismatch in mechanical properties between conventional electronic materials and biological materials. And so I think we all probably have a good intuition about this mismatch. So for one, electronics typically are very stiff and difficult to bend, while biological systems are usually comprised of soft and flexible biological tissues, where kind of the extreme example is brain tissue, which you can think of as being as soft and squishy as Jell-O. Another mismatch is in terms of stretchability, where typical electronic materials can't really be stretched to any significant degree. If you tried to pull on a silicon wafer, for instance, you would probably just end up with it fracturing into a ton of little pieces. But on the other hand, because your body is always kind of in motion, whether it's your heart beating or your limbs moving around, these soft and flexible biological tissues that make up the body are also quite adept usually at accommodating tensile strains. And so in my talk today, I want to focus on these two properties of stiffness and stretchability. And in each section, I'll motivate why these are important for us to think about when we're designing materials for that bioelectronic interface. And I'll then share how I've approached bridging these gaps through my work developing new conductive hydrogel materials here at Stanford. And in particular, I'll show that by just processing and manipulating a very common commercially available conducting polymer, we can make conductors that have tissue level stiffnesses as well as high stretchabilities and orthogonally controllable mechanical properties. So to start with, I'll talk about how we can make tissue level stiffness conductors by forming hydrogels out of this conducting polymer. In the first part of this section, I'll discuss how with different rationally selected additives, we can make gels that are not only super soft, but also highly electrically conductive. And then in the second part, I will discuss how by leveraging different gelation kinetics in the presence of these different additives, we can pattern these conductive gels in two distinct ways. So as I mentioned, there is this huge stiffness mismatch between conventional conductive materials and soft biological tissues, with brain tissue kind of being on the very extreme end of this spectrum. And when I talk about stiffness, I will often be referring to elastic modulus, which is kind of the main figure of merit describing that property. And one of the reasons why this stiffness mismatch is problematic is, first of all, it makes it very difficult to have long-term stable interfaces between electronics and biological systems. So for instance, if you take a rigid metal electrode and implant it into your soft brain region, then it's now really well understood that that stiffness mismatch elicits an inflammatory response which leads to glial scar encapsulation of your device, as shown here by the high density of cells surrounding the implant. And so over time, not only does this lead to loss of your device functionality, but in the worst case, it can actually cause damage to the patient. And then on a more local level, cellular biologists now also have really good understanding of the various mechanotransduction mechanisms by which cells can sense and respond to the stiffness of their surroundings. So especially for these regenerative medicine applications that are interested in using electrical functionalities, you can imagine that if you take a cell and interface it with something that is now tens of millions of times more stiff than the native tissue environment, then that can really have negative impacts on the differentiation, spreading, and migration behavior of the cell. So one way we can address this mismatch is to work with hydrogels, which comprise a very high content of water, up to 99% in some cases. And since we can think of water as a plasticizer for the polymer chains, hydrogels actually often have elastic modulus values that are kind of within the same range as what's observed for soft biological tissues. And that's part of the reason why our bodies are already really used to intimately interfacing with hydrogel materials in our day-to-day lives, whether it's in the form of contact lenses that we put in our eye or various cosmetic products like facial masks. And so to make a hydrogel electrically conductive, the main kind of design principle we came up with is that you have to form these macroscopically connected networks that can transmit electrical charge throughout the bulk of the material, while still maintaining that high water content that we want to achieve these tissue level modulus values. And so the way we do that is by working with a conjugated polymer system called P.PSS, which is probably one of the most commonly used conducting polymers in the biomedical space because, first of all, it's commercially available with really good reproducible qualities. It has demonstrated biocompatibility, and it has relatively high conductivities compared to other conjugated polymers. And P.PSS is actually this two-component system where P. here is the conjugated polymer, which, because it has alternating double bonds along its backbone, can actually transmit electrical charges. And then it's complexed with PSS, which acts both as a dopant for the P. and as a way to disperse this in water. So the P.PSS that you can typically purchase from vendors is usually an aqueous dispersion of about 1 to 2 weight% of the polymer in water. And if we look at what this looks like in solution, the P.PSS forms these kind of dilute microgel particles whose primary interparticle interaction is electrostatic in nature and really driven by these repulsive forces between negatively charged sulfonate groups on the PSS. And so that's why the microgel particles can flow past one another and behave as a viscous liquid. When you increase the ionic strength of these solutions, you can screen those electrostatic repulsions and actually get the P.PSS microgels to aggregate into a physical hydrogel. So here, for instance, we've mixed P.PSS solution with 10% of a 10x concentrated phosphate buffered saline solution so that the final concentration is about the same as regular PBS. And we see that as we mix, the zeta potential increases, showing that we're screening those repulsive effects. And the resulting material is this solid-like opaque hydrogel, where we can get a little bit more insight into the mechanical properties by doing oscillatory rheometry. So here on the right axis is tan delta, which is kind of a ratio of how liquid-like to how solid-like the material is. And so we see that after aggregation, you're forming a material that has a tan delta way less than 1, indicating that you're sufficiently able to form this polymer network so that it's behaving like a solid within this frequency range. On the left axis is storage modulus, which is proportional to like how stiff or elastic the material is. And here we can see that because the polymer concentration is so low, we're able to obtain these values of around 100 Pascal, which is ultra low on the low end of that region we want for biointerfacing. And so these properties were interesting to us because from the rheology, it seems that we can directly form this gel network just from this conducting polymer. And so based on our design principle, we then wanted to test the electrical properties to see if that indeed correlates to good electrical conductivity. The way we measure conductivity is by sandwiching our gels between 2 gold electrodes. And then first we just apply a constant voltage across the gel and then look at what the current response is. But unfortunately, we see that we just get a transient current that quickly drops to near zero, indicating that there's really negligible electrical conductivity in this gel. To get a little bit more insight into what's going on, we can do electrochemical impedance spectroscopy, where now instead of applying a constant voltage, we apply this AC voltage. And then the impedance, which is the ratio of voltage to current, gives us information not just from the magnitude of the current response, but the phase shift as well. And really briefly, what you can tell from these sorts of measurements is that if your measurement circuit is looking like a resistor, then you'll have a frequency independent impedance with a phase shift of 0, whereas if it's more like a capacitor, you'll have a frequency dependent impedance and a phase shift of -90. So if we do the same type of measurement with our gel, then here in the pink, we see that the impedance profile basically resembles that of just a purely ionically conductive PBS electrolyte. So for both cases in this high frequency range, what we see is that the phase shift is around 0 with a low frequency independent impedance. And that's indicative of there being these ionic charge carriers within the material that can enable the circuit to look like a resistor at these higher frequencies. But once you get to lower and lower frequencies, those ionic carriers start to saturate at the electrodes, and it begins to resemble a capacitor, which is why you have this really dramatic impedance increase. And so based on this, we can see that just by forming a gel network alone is insufficient to have good electrical conductivity, and the gel that we've tested is purely just essentially an ionic conductor. And so with that observation, we were really interested to see if we could manipulate the morphology of these gels to enhance conductivity while maintaining that ultra-low storage modulus. And based on our group's knowledge of how to make and process P.PSS films, we hypothesized that if we could form P.PSS hydrogels with rationally selected ionic additives, then perhaps we could make much more electrically conductive gels as well. In particular, what our group has previously shown is that if you blend these ionic liquids with P.PSS and then spin coat them into films, you actually can observe really dramatic increases in conductivity. And these conductivity enhancements correlate to a change in the film morphology from kind of this ill-defined grain structure to having these extended fiber-like morphologies where the fibers are comprised of crystalline P-dot units whose crystal spacing distance is comparable to the pi-pi stacking interaction distance between different conjugated P-dot polymers. And to understand really why this phenomenon occurs, there was a really nice recent study from Kwang-hee Lee's group at the Gwangju Institute of Science and Technology in Korea, which showed that basically it has to do with P-dot and PSS being a two-component system. And so different additives can disrupt that interaction to varying degrees via counter-ion exchange. And so the more effectively that an ionic additive can do counter-ion exchange with P-dot and PSS, the more effectively you can liberate P-dot to phase separate into these more ordered structures that conduct electrical charges over more extended length scales, thereby enhancing conductivity. And so based on this, we were really curious to see that if we formed hydrogels with one of these conductivity enhancing ionic liquids and compared it to hydrogels made with the salts in PBS, which don't have any sort of conductivity enhancing effect in films, if we could see some differences in these hydrogel states as well. And indeed, we find that in both cases, we can make materials that have very similar mechanical properties. So both still have these ultra low storage modulus values and 10 delta values of less than 1. But now if we look at the AC impedance spectra of the ionic liquid form gel, we have this really low frequency independent impedance with a phase shift of about 0, which indicates that now, even at this low frequency range, you're getting electrical charge carriers that can still enable that resistive behavior throughout the entire range of tested frequencies. And taken another way, if we apply a constant voltage across these materials, then now we can sustain a significant current, which enables us to see that these materials have 5 orders of magnitude higher electrical conductivity than their PBS form counterparts, despite having really similar mechanics. And so with that, we propose that there's 2 types of conductive gels that we can form, where in the first case, where you're just screening those electrostatic repulsions and getting microgel aggregation, you're not actually changing the internal structure of those gels, and you end up with something that has very poor electrical conductivity. Whereas if you use these additives that can undergo counter-ion exchange with P dot and PSS, then you can form these much more electrically conductive gels, which we think probably has a similar type of internal structure as the thin films. And we still maintain these ultra-low elastic modulus values because of the high water content. And aside from blending with these conductivity enhancing additives, another way that researchers have previously enhanced the conductivity of P.PSS films is by using post-treatment methods, where they'll start with like a spin-coated film of P.PSS and then rinse them in acidic solutions of things like acetic acid or sulfuric acid. And here the mechanism is really similar, where the preferential interaction of the proton with PSS minus neutralizes the PSS so that P dot is now freed up to phase separate into those more conductive morphologies. And you can actually visualize this process using X-ray photoelectron spectroscopy, because there's a unique sulfur environment on PSS and on P dot, which means you can track the ratio of these two components. And so what people see is that after rinsing with these acidic solutions, you actually, because you've liberated some of that PSS from its attraction to P dot, you can remove some of it through rinsing, and you get a relative increase in the P dot to PSS ratio. So based on this, we were also interested to see if post-treatments could enhance hydrogel conductivities as well. And to test that, we fabricated those low conductivity gels with PBS and immersed them in different concentrations of acetic acid overnight, followed by neutralization in regular phosphate buffered saline to account for differences in pH. And as we expected, the acetic acid treatments also dramatically reduced the impedance of our gels as a function of concentration, as well as changing the phase angle from these low negative values to near zero. Analogous to the thin films, we also see that this post-treatment can allow us to remove some excess PSS, as seen by this relative increase in P dot to PSS ratio again. And finally, as we lower the impedance of the gels, we're also increasing the storage modulus, which suggests that these new conductive junctions that are being formed in the material are directly also contributing to the elasticity of these polymer networks. So therefore, just like we can directly form these highly conductive gels through blending with the ionic liquid, we can also take something that's less conductive and use post-treatment methods to enhance the conductivity of these already formed soft gels. So now that we have an idea of how to design these electrically conductive soft materials, the next thing I want to talk about is how we can leverage different gelation kinetics to actually pattern them in different ways. The first way came about when we were working with those conductivity enhancing ionic liquids, and we noticed that compared to other additives like metal salts or acids, the gelation of P.PSS in the presence of these ionic liquids happened over relatively long timescales. To test this, we can mix the solution with ionic liquid and then use a rheometer to monitor the gelation time. And what we see is that there's actually a relatively large window of time where the loss modulus here in light blue exceeds the storage modulus, meaning that this mixture is behaving like a flowable liquid. And so this is pretty beneficial because it means there's enough time to take these precursors and pour them into different molds so that we can directly mold these highly conductive freestanding shapes for things like patches or electrode pads, which could be really useful for doing things like taking electrophysiological measurements throughout the body. On the other hand, if you want to have more miniaturized devices that might include multiple layers or materials or components, then we want a different type of fabrication method besides molding that might be more amenable to these kind of more complex device integration processes. And so to enable that, we wanted to see if we could come up with a method to better control the spatial deposition of our P.PSS gels on different surfaces. So we came up with this concept of using a sacrificial metal layer that we could oxidize in the presence of these P.PSS solutions, generating metal cations that would screen those repulsive forces between the microgel particles and get it to aggregate into a gel. And so here is where we can take advantage of those post-treatment processes to enhance conductivity, so that the main important step is just being able to shape those physical gels into your desired pattern to begin with. And with this concept, we came up with a method that we call electrogelation patterning, which has the main advantage of allowing us to leverage now commonly used metal thin film patterning techniques, including evaporation through a shadow mask. And as long as you can pattern that sacrificial metal into your desired shape, then you can use electrogelation to convert those patterns into the patterned P.PSS hydrogel. For the sacrificial metal, we decided to use copper because it's easy to electroplate or evaporate onto a variety of different surfaces. And if you look at the Pourbaix diagram of a copper water system, you can also see that there's a pretty large window of voltages where this cationic form of copper is the equilibrium species. Moreover, that's happening within the water stability window, which means that you can oxidize the copper without worrying about the side reactions that might generate gaseous byproducts, which we've actually seen can physically damage the gels that are formed. So then with this copper-coated surface, we can use that as a working electrode within this cell where the electrolyte is the aqueous P.PSS solution. And so we just apply a constant voltage somewhere within this window, and that oxidizes the copper layer into metal ions that result in the generation of these P.PSS hydrogels. One of the really important things that we observed here was that in the presence of copper 2+, P.PSS gelation happened pretty much instantaneously. So this is the same type of measurement that I showed before with the ionic liquid, where we were trying to monitor gelation time. But here, because it's so rapid, the moment we start taking the measurement, you're already having this solid-like behavior with storage modulus exceeding loss modulus. And so we think that in the case of this patterning method, fast gelation is actually really beneficial because it enables us to retain the fidelity of the original sacrificial pattern, since those ions don't have enough time to migrate from the surface before the gel is formed. And so combining this fast gelation with our sacrificial strategy, we now have a really simple way to create high resolution features like this shown here, where the smallest features lines are 100 microns in width. But not only that, because the way this gel is formed is just through aggregation of these microgel particles, we can still maintain the high porosity and high water content that we need to get our desired mechanics. And finally, since electrogelation is the surface-based method, not only can we make these high resolution features on planar surfaces, but we can also readily pattern onto curved substrates. Or if we use electroplating instead of evaporation, we can also really easily generate these conformal hydrogel coatings while maintaining the 3D structure of whatever we're trying to coat. And so this just expands the options overall for how we can integrate these conductive materials into devices that might have different or unconventional geometries. So overall in this section, we see that one, through the rational selection of additives that can undergo this counter-ion exchange with P.PSS, we can form these soft hydrogels that also have really high electrical conductivities. And these additives also impact gelation kinetics, where slow gelling ions are really good for molding-based fabrication processes, whereas rapid gelation in the presence of these metal ions allowed us to come up with this new patterning method that not only creates high resolution feature sizes, but also these conformal gel coatings. So now that we've talked about how to make these soft conductive networks, the next thing I want to talk about is how to make them stretchable. And here I'll show that we can build on these soft conductive gels and use the concept of interpenetrating polymer networks to make conductors that are not only highly stretchable, but that also have orthogonally controllable mechanical properties. Now, the reason that we care about stretchability is because many of the surfaces within the body that we would want to transmit signals across are dynamic and in motion. So for instance, the surface of your heart actually experiences a lot of strain as it beats and contracts. And your skin experiences significant strain just from motion, like bending your arm. Even your brain, that you don't typically think about as being in motion, actually does experience quite a bit of displacement at rest just from respiratory activity alone. And so to create electronics that can conform to these moving surfaces, engineers have come up with a variety of really clever strategies to make stretchable electronics. One really common approach is to have the electronic components be used as rigid islands, separated by interconnects that have been made stretchable using geometric strain engineering techniques. So here, John Rogers uses these serpentine interconnects, and then Takao Sameya likes to use these kind of mesh-like structures. But the limitation with this engineering approach is that It's really highly dependent on the dimensions of your device, and you also typically need pretty large amounts of distance between those rigid islands to accommodate strain. And so there's an inherent limitation there in terms of how complex or dense you can make these electronics. And so for future electronic devices, there's been a real interest in creating intrinsically stretchable conductive materials to kind of overcome these limitations. To that end, researchers have used strategies like plasticizing with small molecule additives to make conducting polymers pretty highly stretchable. But despite all of that, the stiffnesses of these stretchable conductors are usually kind of on the higher end of what we want, around 100 megapascal or so. And so going back to the first part of this talk, one of the really easy ways that we can make tissue level soft materials is with hydrogels. And indeed, there's been a lot of reported hydrogels that are highly stretchable and tough. At the same time, examples that have taken these stretchable gels and just kind of blended in some conductive additive typically report low conductivity values of less than 1 Siemens per meter because they're not deliberately forming this conductive network. And so the question that we asked ourselves was, how can we leverage these known hydrogels that are soft and stretchable and combine it with what we know about making soft conductors in order to make hydrogels that are simultaneously soft, stretchable, and conductive? To solve this problem, we wanted to see if we could make interpenetrating network hydrogels, where one network is the soft and conductive P.PSS gel that we described in the first part of this talk, and the other one is a stretchable hydrogel. And so as a proof of concept, we decided to make polyacrylic acid gels, which can be easily stretched to over 250% strain, and that have elastic modulus values that are kind of within this kilopascal range of interest that we want for biointerfacing. For the conductive network, because we don't want to increase the overall modulus too much beyond these values, and because we want to be able to mold freestanding films for mechanical characterization, we decided to make P.PSS networks using the ionic liquids that I talked about before. And so to actually interpenetrate these two networks, we start by molding the soft and conductive P.PSS gel, and then backfill the gels with acrylic acid monomers, bisacrylamide as a chemical crosslinker, and then this thermal initiator that activates at 60 degrees C. And so after heating, we then have this polymerized polyacrylic acid, and the resulting material we call CIPN, or conductive interpenetrating network gels. These CIPN gels are stretchable, soft, and conductive with values above 10 Siemens per meter, which is significantly higher than these previously reported examples that just kind of incorporate conductive additives without forming that network. But more importantly than that, we see that we can, just by changing the ratio of acrylic acid monomers, tune the elastic modulus over 3 orders of magnitude, all while maintaining the conductivity within the same kind of order of magnitude value. And so this is because we've decoupled that electrically conductive network from the one that's dictating the mechanical properties, meaning we now have this orthogonal lever to be able to tune the mechanics without having to worry about compromising on the electronic properties. Also important is that these CIPN gels have stable conductivities with strain. So here we see that the electrical resistance across the gel stays pretty constant even when cycling back and forth between 0 and 100% strain for 10 cycles. And we think that's because there's a lot of water embedded in these materials, meaning there's a lot of free volume for the polymer chains to be able to accommodate strain without having to actually break down the conductive network. And finally, we can pattern these CIPN gels using the same methods described previously, where with the ionic liquid, we can mold them into different shapes, like these micropyramids that were made with a silicon wafer mold. And after you have the molded conductive network, you can backfill them with monomers and polymerize them in this very same way to make these stretchable gels. But we can just as easily increase the complexity of what we can make by using electrogelation, where, for instance, we can pattern this X shape and then backfill them with monomers. And if we polymerize it together with the bath, then not only do we have this stretchable conductive pattern, but we have something that's also intimately integrated with that stretchable hydrogel substrate underneath. So ultimately, I think that the main advantage of this kind of interpenetrating network approach is that it allows us to take advantage of all of the exciting developments that are happening in the field of hydrogel materials. Because moving forward, we can imagine replacing that polyacrylic acid network with other networks that exhibit different functional properties beyond stretchability. So here's where I really think that there are exciting opportunities for chemists to think about what sort of new functionalities might be important at the bioelectronic interface. Just as a quick example, there are all of these exciting hydrogels that have been reported with tissue adhesive behavior or stimuli responsive behavior, or gels that incorporate cell adhesive ligands to promote integration of cells into the material. And so with this interpenetrating network design, we now have, I think, a pretty simple path to start thinking about incorporating these sort of next generation functions into our conductive materials at the interface of your electronic device and your biological system. So overall, I hope I've shown that, first of all, through different patterning strategies and processing strategies, we can obtain these highly conductive materials that have tissue level stiffnesses and broad patternability for a variety of different applications of interest. And then once you have that conductive network formed, we can then orthogonally tune mechanical properties of interest, including stretchability, through the use of these interpenetrating polymer network designs. So I just want to acknowledge Professor Bao, who has been my incredible advisor during my time at Stanford. She runs a super huge interdisciplinary lab of over 50 people, and it's just a really great environment to work in. And I especially want to acknowledge my main collaborators on these works, Dr. Helen Tran, who is an amazing chemist and starting her faculty position at the University of Toronto in January, Dr. Mina Lee, who is an amazing electrochemist, who now runs a group at the Korean Institute of Science and Technology, and Kathy Liu, who is the undergrad who's been working with me for the past few years and who's super talented and applying to grad schools next year. So with that, I want to thank all of you for your attention. Thanks for accommodating the schedule change, and I will be really happy to answer any questions that you might have.
Thank you, Vivian. It was a very beautiful talk and very exciting. I mean, I learned a lot. So with that, let's take the questions. So we have one question from Antonio. He says, congratulations, very interesting talk and work. So he asked, can you electrogelate another P dot doped solutions like P dot and hyaluronic acid, for example?
Yeah, it's a really good question. I haven't tested it myself, but I imagine it just depends on the gelation mechanism of that new system. But for instance, we have tested electrogelation with sodium alginate, which can also be cross-linked with these multivalent cations, and it seems to work just as well. So I think as long as somehow your polymer system is cross-linkable with these divalent cations, then you should be able to apply this patterning method to pattern that as well.
Excellent. So we have another question from Sai. He asked, is it possible to dope these basically hydrogels you make with graphene-like materials to increase the conductivity?
Yeah, I think so. I mean, that would basically be like incorporating more conductive additive to enhance conductivity. But I guess the trade-off would be you would increase your stiffness as well. And so I think it's definitely doable. And if you have specific conductivity targets that you're trying to meet, then that would be a simple way to boost it a little bit to achieve that. Mm-hmm.
Perfect. So we have another question from Chunyan. Sorry. He has a question that how do you remove sulfuric acid from hydrogen to do the testing from the hydrogen?
Mm-hmm. Yeah, so with these porous gels, just by immersing them in these baths of neutral PBS buffer, we can just exchange it out until the pH is neutralized. And so we see this also with like the electrogelation process where we have these copper ions. With just rinsing, we can eventually remove the copper so that it's not detectable via any kind of spectroscopic method. So I think the important thing to note is that the gels that are actually formed, the actual network doesn't include these additives. They just induce the gelation. And so the gels themselves are stable even after you rinse away the additives that were used to induce the gelation.
I see.
Mm-hmm.
Perfect. So we have another question from Sipe. He's an alumni. Good to see him. Is it possible to quantify electron conductivity only using EIS?
Um, can you clarify what you mean? Like to
I,
decouple the electron versus ionic conductivity, you mean?
I think he's talking in terms of the technique,
Hmm.
EIS technique, and he's saying, is it possible to quantify electron conductivity only using this technique?
Yeah, I think so. So actually, if you look at the Nyquist plot instead of the Bode plots that I've showed, um, you can kind of fit them to, well, I guess it doesn't really matter what you look at, but you can fit them to an equivalent circuit. And then there's a lot of software that you can use to kind of extract different types of resistances. And so I think in principle, it is possible to do that in a more quantitative way. But I think just even qualitatively, what we see is that at lower frequency values, the resistive behavior that you get is due to electronic conductivity because the ionic charge carriers kind of stop contributing to that.
Perfect. So if you don't mind, we have a few more questions. Let's take them. So we have another question from Hamid Tagipo. He asked, can you comment on the ion aggregation? Did you measure wax, yeah, WAXS?
Yeah, that's a great question. So I don't know, I don't think there's really a lot of ion aggregation in the materials, but it would definitely be interesting to be able to quantify the P dot aggregation. And so for the films, people indeed do wax studies to show that as we're getting this more conductive morphologies, you're getting these crystalline you're getting these kind of crystals that are forming due to the aggregation of P dot polymers. And so I have just kind of shown like a correlation based on the electrical properties that we think there's probably similar types of aggregation happening in these gels. But moving forward, I definitely think doing those kind of measurements would help to confirm that in a more rigorous way.
Perfect. So we have another question from Ming Kang. It's on the similar, I mean, I also have a similar thing, question that how do
Yeah.
you maintain such high water content and prevent the hydrogel from drying?
Yeah, no, that's a great point, and that's definitely one of the challenges with working with hydrogels. But there has been some really recent exciting work where multiple people have shown that you can just encapsulate these gels with some kind of elastomer, like a non-hydrogel elastomer, using by like cross-linking it into some polymer system that's embedded within the gel. And so people have shown that these types of encapsulation processes are really sufficient to be able to prevent it from drying out. So that's definitely especially important for these like on the body applications where drying would be a big concern. But beyond that, I think for all of the in vivo applications, then we're not as concerned about drying out.
Okay, perfect. So let's take the last question then. Benjamin asked, how does conductivity and modulus scale with temperature? Are the hydrogels as effective in the body environment? I think.
Yeah. So the mechanical properties that I've tested were all at body temperature, and I'm not entire. I don't know exactly the answer for how it scales with temperature, but I don't think we've observed very significant differences just between room temperature and body temperature. In terms of the conductivity, I do agree that that would be important to test, but I don't have an answer at this time. But I don't imagine the difference between room temperature and body temperature would be huge, as long as you're kind of staying within this range before water starts to evaporate.
Okay, we have two more questions. If you don't mind, let's, so that they don't feel bad.
Mm-hmm.
Perfect. So we have another question from Vidika Damani. She asked, what are some means to remove the unreacted monomer after the conducting interpenetrating network is formed?
Yeah, so this is kind of the same thing as the person asked before about the sulfuric acid. You can just rinse them with like PBS solution to get rid of the monomer. And we've shown that that's sufficient to get rid of it, to at least to undetectable levels.
Perfect. Okay. So with that, let's, thank both the speakers. It was a very interesting session, very learning experience. Thank you very much to everybody in the audience for joining us. And we hope to see you next Wednesday, where we discuss more on the mechanistic aspect of things. With that, thank you, everybody.